Welcome back, physicists. This week, we are going to be solving for the mass of a black hole by studying the trajectory of a star that is orbiting the black hole. So first, what do we know? We have the momentum principle, which tells us that the final momentum is equal to the initial momentum plus a net force times delta t. Hence, the change in momentum over time is equal to the net force. We also know the mass of the star, which is 1.98 times e to the power of 30. We also have our gravitational force, with a gravitational constant that is equal to 6.67 times 10 to the power of negative 11. And the magnitude of that gravitational force is the gravitational constant times the product of two masses times the direction, r hat, times the magnitude of r, the magnitude of the distance between those objects squared, or the radius between those objects squared. So, what are we going to be doing in Python? We are solving for the mass of the black hole, which we find to be 1.99 times e to the power of 31. In order to solve for the mass of that black hole, we take the magnitude of F net times the magnitude of r squared divided by the gravitational constant times the mass of the star. In Python, our code will look something like this. So what did we have to edit in Python? First, we edited the mass of the star. Second, in the introduction to the lab, we were told that the time interval of each measurement of the star's position in its orbit was taken every day. So we have 86,400 seconds in a day. Finally, we set the black hole position to the origin. Then, we use the Excel data to solve for the following: the change in velocity, the change in momentum, and the net force. So, our Python code will look something like this. Here, we read in the data from the CSV file that was given, solving for the velocity in the x direction and the velocity in the y direction. And then, using these, we solve for the initial velocity, final velocity, initial momentum, and final momentum. And then down here, we finally get into the change of velocity and the change in momentum. And then we find dp, F net is equal to dp dt. And then ultimately, what we're really interested in solving for is down here. Once we have all of our information for F net, the position of the star, and the mass of the star, we can finally solve for the mass of the black hole. So if we run our Python program, we should get something that looks like this. First, the black arrow represents the parallel momentum, The blue arrow represents the perpendicular, the direction of the momentum. As we can see, that is pointing towards the center of the kissing circle. And then the yellow arrow is representative of the net force. So, to answer our two questions, what does it mean? How are F net perpendicular, F net parallel, and F net different from delta P and delta T, delta P parallel, and delta P perpendicular? Well, first, let's think about how they're different. We know that they're equal, but we also know that you can solve for dp over dt, which is the derivative of, and that's the derivative of dp over dt is just the change in the magnitude times the direction, and the change in the direction times the magnitude. Those will give us our parallel and all perpendicular components. So really, what the change in momentum is telling us whether or not the star or the ball is speeding up or slowing down in the direction of that change. So F net is just telling us what's causing the momentum in the first place. And you can see that you can solve for F net by summing up different forces, like a weight force, a drag force, and a gravitational force. So that then begs the question, well, why are they equal? Well, that's because The change in momentum is being caused by the force, the net force, and so they ultimately have to be equal. Finally, the what if you imagine a black hole whose mass you have found was replaced by a different black hole, but still placed at the same location. If everything is still the same, the star's trajectory is still the same, and is affected only by the gravitational force of the new black hole, could you tell the difference? No, you actually really couldn't, because everything is still the same about the trajectory of the star. And since we only have one gravitational constant, everything else would still be the same. So if the masses are different, there's no way to tell, given what we know.